Hello everybody. Today I will be demonstrating how to use the BioAwk tool. BioAwk was written by Henley, the same author of the SAM tools and the BWA aligner. So thank you very much for this beautiful tool to the bioinformatics community. I also would like to thank Arun Sidaram because he compiled the command lines that I will be presenting to you today, and I recommend you visit his bioinformatics workbook because he has a lot of cool things there. All right, so the first trick I will be demonstrating to you is how to extract the length of each sequence in a FASTA file. For demonstration purposes, I have here a FASTA file that is called bacteria.fa, and you can see that it contains a series of fragments of sequences of bacterial genomes. So we will be extracting the length of each of those sequences here in the first trick, and for that we will call BioAwk, and you pass the flag C to indicate the type of file. FastX includes FastA and FastQ files, and then we start with an awk command, and we'll say here print a variable that BioAwk stores automatically, which is called name, and it contains the IDs of a FastA file, and then we will then include a comma just to separate the two fields, and we will use the function of awk length, and we will pass another variable that BioAwk generates automatically, which is called seek. And this is pretty much all what we need to generate the length of each of the sequences in a FASTA file. And here we see. Okay. Please notice that IDs are truncated at the first space that is encountered in the ID. So if you want to prevent that, you will have to substitute those spaces by any other character that you want. To calculate the percentage of GC in all sequences in a FASTA file, we will again call BioAwk and specify the format FastX, and then we will just print name, and we'll call a BioAwk function that is called GC of seek, and we are done again. And you will see here that instead of the percentage, what we have here is rather the proportion. So if you want to convert that to actual percentage, you can multiply the result of the function gc by 100, and now we have the percentage of gc in each of the sequence of the FASTA file. We will now produce the reverse complementary sequences of a whole FASTA file. So we will do that again with BioAwk, indicating the format of the input file, and then we'll just print greater than sign just to preserve the native FASTA file, the name of the sequences. Sorry. Then we will introduce here a new line character here, and then we will call a BioAwk function that is called reverse comp of the sequences, and pretty much that's it. Now we will extract only sequences that fulfill a specific condition. Let's say we want to extract only sequences that are longer or equal to 150 base pairs. So what we will do here is that we will say length of sequences is greater or equal to 150, then print name. We can introduce here the greater than sign just to preserve the native FASTA format, then a new line character, and then finally the sequence. Oops. And now we see that we have extracted only sequences that are equal or longer than 150. Let's say we want now to modify the ID lines of a FASTA file. So what we can do is we can print, for example, a greater than sign. We can include here any prefix we want. Let's put another space here. And then we will add the existing ID, a new line character, and then the sequence. And you see that we have added here a prefix at the beginning of the ID, right? If instead of a prefix, what we want to add is a suffix, then we do that in a similar manner, right? And then we can write here the suffix, and then you will see here that at the end of the sequence we have added a suffix. Of course, prefix and suffix will be replaced by these strings of interest. Now the next trick. So here what we want to do is we want to convert from FASTA format to a tabular format, and instead of specifying only the format of the input file, we specify here the format of the output file. And we will write here that we want to have the name of each of the sequences and a comma to separate the two columns, and then the sequence. And you see here that we have generated a table with two columns. The first column contains the ID, the second column contains the sequence. Here comes the last trick. Pay a little bit of attention because this command is a little bit tricky. So what we want to do here is we have these two IDs in a file that we call IDs, and we want to extract the sequences corresponding to these IDs in the FASTA file. So to do that, we will call BioAwk again, and we will specify that the format of the input file is FastX, and here we will start begin a while loop, and we will call here an awk function that is called getLine to read the different lines of our file that contains the IDs, which is precisely called IDs. And then this is the way awk has to say that the line of a file contains a value, and an array will be created for each of those lines, and if the line is there, then the array will have a value of 1. If it is not, it will contain an empty slot, let's say it in that way. And then we will set up a conditional here. Then we will say if the array of that matches the name, or the other way around, if the ID of a sequence contains the string in the IDs file, then we will print the name. Probably if we want to preserve the native structure of the FASTA file, we do it this way. Then we introduce a new line character here, and finally the sequence. And you see here that effectively we have extracted the sequences corresponding to the two IDs that we had in the IDs file. Apologies for the cryptic form of this command line, but unfortunately that's the way the awk syntax works. So I know that the command line was longer than the segment of the screen I was presenting in my video, so don't worry about it. Here is the command again that you can see it complete and copy it if you need.